We need to explore is the idea of scientific notation. Once again, this is nothing new. I believe you started learning this in the sixth grade. But scientific notation is really important when we talk about chemistry because we deal with numbers that are really, really, really large, like the number of molecules, and numbers that are really, really small, like the mass of an electron. So whenever we look at it in numbers that are really big and really small, it becomes really important that you be able to convert and enter these numbers on your calculator. So the first thing you see is you see that this number right here is really large. That's actually the mass of the Earth. So really what we want to do is we want to be able to express these in an easier way to write. And so the rules that we have for that are this. You need to be able to get the number between 1 and 10. Okay, and it really shouldn't be 1 equals to 10. That's exactly right. It should be like that because you can't have 10. Okay, you could have 9.99999, but you can't have 10. Okay, so the number has to be between 1 and 10. The next thing you look at is n has to be an integer. Okay, we want this to be a number, not 1, 2, 3, 4, 5, or -1, -2, -3, but we do not want 1.5. At some point we'll use those in terms of math, but that's not what we're looking for when we talk about scientific notation. And finally, n is determined by the number of places the decimal must move in order to make it a number between 1 and 10. So if we go back to our original examples right here, we start off with here's the decimal. We'd have to move it over 3, 6, 9, 12, 15, 18, 21, 24 spaces. So the mass of the Earth can be reported as 5.98 times 10 to the, I moved it this way, 24. Now the easiest way to remember whether this is a positive or a negative number isn't did you move it left, did you move it right? That can be kind of confusing. You ask yourself, is this a number bigger than 1? If it's a number bigger than 1, then you're going to have this 24, or it's going to be a positive exponent. Now right here you see this is a number that's less than 1, so it's automatically going to have a negative exponent. So we do the same thing. We do 3, 6, 9, 12, 15. You keep doing it. It ends up being 9.11 times 10 to the minus 31st. Okay, number between 1 and 10, whole number. Number between 1 and 10, whole number. So let's look at a couple of examples. And the first one says the mass of a proton is 1.672 times 10 to the minus 27th. It says write this number in standard notation. This is just getting the idea of going back and forth. On a test, you will never be asked to write a number like this out. So let's do it the one time and be done with it. You see 1.672. And then what you need to do is you need to move it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Okay, and then you fill in each one of these gaps. Whenever you fill in each one of these gaps, you should end up with about 26 zeros after the decimal point. Okay, I'm not going to fill all those in because it gets to be pretty tricky at that point, but you moved it over 1, and then every other time that you added it, you added another 0. So this is an exceptionally small number. It is the mass of a proton, which is another reason why we need to master scientific notation. It says a cesium-133 atom vibrates at 9,192,631,770 times per second. It says identify the time of a single vibration in scientific notation. So this is an interesting question because if you look at it, this is the number of times it vibrates per second. And I want to know how many seconds it takes for a single vibration. So what I want to do is I actually want, if you look at it in terms of units, I'm reporting it as, we'll call it oscillations per 1 second. And I want to flip these two because what I really want is seconds per oscillation. And so what I do is I actually flip these two, put one on the top, that on the bottom, and I can enter it in my calculator. And whenever I enter it in my calculator, you end up getting a value of 1.09 times 10 to the minus 10th. Now before you move on from here, you really need to take time to figure out how your calculator works. If you're using a TI product like a TI-83, 84, any of those sorts of things, you really need to be able to be using the second comma key. The second comma key, which is just above the 7 whenever you're entering things in scientific notation. You would enter 1.09 second comma, which would give you this E, and then you'd enter minus 10. Okay, that right there is the proper way to enter it into a TI-83, 84, whatever you're using. Okay, do not do 1.09 times 10 to the negative e or caret negative 10. Whenever you do this, you are throwing off the order of operation. So we are not going to do that. Always use the E key whenever you're doing scientific notation. So now, we look at significant figures. Significant figures is what kind of fell by the wayside a lot of the time as we move through the year in chemistry. It is very important that you report significant figures, okay? Because what it does is it reports the degree of uncertainty in your answer. So how correct is your answer? So if I said your grade was somewhere between 90 and 100, some of you would be happy with that, that's good. But what if I would report it as somewhere between 70 and 100? The degree of measurement is not there. I mean, you could have a 70, you could have a 100, but nobody knows. So what we're trying to do is we're trying to narrow that window as much as possible and say your grade is between a 95.4 and a 95.6. Okay? Even that has some implications on whether or not you get a 95 or a 96, but you need to lower this degree of uncertainty. Whenever you just put an answer as 2, well, does that mean it's 2.0? Does that mean it's 2.00? Does that mean it's 2.0000000? Nobody knows what degree of accuracy you used unless you report the significant figures. Because of that, significant figures are always included in scientific research. And this is where it gets really tricky. You can't take a number like 1 and divide it by 6 and say that the answer is, I don't know what that is. I feel like it's 0.1666667. You can't report that degree of accuracy because you didn't measure out this far. Really, the more likely answer that you would have to report is 0.2 because you can't report all of these numbers. Now, more on the rules later, but this is really important right here. You will lose 1 point automatically if your answer is not in significant figures. That is not my policy. That is the College Board policy on any sort of free response question. So because of that, we're going to start to enforce that early so you start to realize these things as you move through. In addition, in the lab, whenever you report something, it needs to be reported in the correct number of significant digits. So, what figures are significant? Digits 1 through 9 are always significant. If you have a number that is not 0, it is always significant. Always, always, always. A 0 is significant if it is between other digits. So if you see you've got a 1 here and a 1 here, everything in between those two numbers is significant. If you have a 0 that is to the right of a decimal place and after a number, like 7.00, these zeros are significant. If it is to the right of a number but does not have a decimal, then they are what are called placeholder digits. In other words, I could report this number as 7 times 10 to the second, and it has the same degree of accuracy. Okay, so because of that, that only has one significant figure. If you were to look here, by reporting this decimal right here, I'm saying that I did measure it out this far, and so the answer is 700 even. So this right here says that these zeros are significant, and if I were to put it in scientific notation, it would have to be 7.00 times 10 to the second, because it has 3 significant figures, which is the same as these 3 significant figures. Okay, significant figures take practice as far as zeros are concerned, but you'll catch on. Whenever you add and subtract significant figures, the process for adding and subtracting significant figures is that you line up all the numbers by the decimal point. So if you look, I lined all the decimal points up right there. And then what you do is you perform the addition or subtraction, and you get the entire number, which is what we have right here. Okay, then you draw a line indicating the last shared digit. So if you were to look right here, the last digit that they all have, the most precise, or excuse me, the most accurate digit that they all have is the ones place. And the reason is this one does not have a decimal. This one only goes to the tenths. But the last one that they all have is that ones digit. So because of that, that is the answer that I report to. And I figure everything after that is used to round to that particular number. If you look, 0.766801 is going to make this thing round up to 1,507, which is the appropriate number of significant digits. If you look, that period, that decimal indicates that I actually measured it to that point. The next one says multiplying and dividing with SigFigs. It says determine the number of SigFigs in each measurement. And then it says constants do not count. And the reason why is even though we report something like Planck's constant to be 6.63 times 10 to the negative 34th, this value has actually been measured with a great deal more precision than that. In fact, it's more common for you to see 6.626 times 10 to the minus 34th, but in actuality, this has been measured out many digits. So whenever you look at constants, don't count constants in terms of the number of significant figures. So when you look here, it says identify the least number of significant figures. This has 2, or excuse me, this one has 3. This one has 1, 2, 3, 4, 5. This one has 1, 2, 3, 4 because that 0 is significant. And this one has 1, 2, 3, but this 0.0821 you should have recognized as being R from Pivnert, which is a constant. Now, if you didn't, don't worry about that. That doesn't come up till later in the year. But if you did, that's great. So really, the number of significant figures that we're looking for in our answer are 3. So you do the math, you multiply these numbers out, you divide by that, and then the answer should have 3 significant figures. So I'm going to go ahead and leave that for you to do, to plug in and round to the appropriate number of significant figures. Now, something that is a little beyond what you did in pre-AP chemistry is how to do significant figures with logs and exponentials. This is particularly useful whenever you look at things like pH. pH is really where this comes into play. So you have to divide something into what's called the characteristic and what's called the mantissa. Okay, the characteristic and the mantissa, the characteristic is not significant. Okay, that basically tells you how many places you are moving the decimal over, whereas the mantissa tells you the degree of accuracy that you are reporting. So if you were to look, I have the characteristic shows how many places you're moving it. So whenever I have the log, this is saying move it over 3 places. These numbers right here are the ones that are significant figures. So this is not an accurate way to report this number because if you look, I only have 3 significant figures in my answer right here. Okay, this 0 is not significant because there's no decimal, it's just a placeholder digit. So really the answer to this top one should be 3.758 because the 1546 does not round up. And if you look, hey, that's 4 significant figures. No, remember this is how many places I had to move the decimal, and this right here represents the 3 significant figures that are in this answer. Okay, so the first number whenever you're dealing with logs is not telling you anything significant about the answer. Only the mantissa is. So let's look at an example. It says the pH measures, the student measures the pH of an unknown acid to be 7.345. So if you look at that, we have this number right here is not significant. Okay, because what that is doing is that's telling me how many digits I need to move my answer. These 3 are significant. So we have 3 significant figures. So whenever I report my answer, the concentration of hydronium ion, it needs to have 3 significant figures. Now you should remember from first year chemistry, if you don't, that's fine, we'll get to it, that pH is equal to the negative log of the hydronium concentration, or the protons. Whenever you take a look at this, you would plug in 7.345 equals the negative log of H plus. We do 10 to the negative on both sides. When I do 10 to the negative, it's going to cause those to go positive, and the 10s actually cancel out, just like you did in math, and you have H plus is equal to, and then at this point you have a number. And the answer should have 3 significant figures in it. So when you report 3 significant figures, the answer should be 4.52 times 10 to the minus 8th molarity. Remember, this and this match as far as how many places did you move the decimal over. These 3 significant figures match up with the 3 significant figures of the mantissa. Now, this one says a student collects 20 liters of gas over 300 Kelvin. The pressure is measured to be 1.25 atmospheres, but water vapor contributes 0.106 at this temperature. How many moles of gas are collected at 0.0821 moles per Kelvin? Now this is an example of a question that we will do later in this year that involves gas laws. And the specific thing that we're going to look for here is called Pivnert. And you're familiar with Pivnert from earlier this year. And you would say N equals, earlier this year, it should have been earlier a couple of years ago, N is going to equal PV over RT. Okay, so you can look at it in terms of we're going to be multiplying and dividing. But before you get to that point, you have to realize that there are two pressures that are reported. Okay, and this is an example of Dalton's law of partial pressure, where the total pressure is equal to the individual pressures added together. Once again, if you didn't remember that, that's because we're not there yet. We will go over all this material in its context, but I just wanted to give you a real example of how significant figures comes into play. So if you were to look, you have the total pressure, and that is 1.25. And then we also have the idea of 0.106 is the pressure 1, and I need to report pressure 2. This is the pressure of the gas that I'm actually interested in. So if you look, I have to subtract these numbers. And when you subtract these numbers, you have to line them up by the decimal point. And when you line them up at the decimal point, you go to the digit that they share. So this would be an example of 1.146. Now that would be my correct answer at this point for the pressure that I'm trying to solve for. But you can only report up to the digit that they share, which is this one. Okay, I'm sorry, got thrown off there. It's this one, the 4. So this needs to round up, and you'd have a pressure of 1.15. So I have 3 significant figures there. I only have 2 significant figures there. And then 0.0821 is a constant. And then you have 300, which has 4 significant figures. So my final answer needs to have only 2 significant figures. And when you do the math and you plug everything in, you end up getting about 0.93 moles of gas.